at this more local scale for plants. What are the drivers of spatial temporal variation in the environmental water that a plant is going to see? And I'll just write a few things on the board as you yell them out. Plants. What's going to cause for this little plant which is growing right outside, what's going to cause variation in the isotopic composition of the water it sees?
Irrigation versus precipitation.
Okay. Precipitation versus irrigation. Good. What else?
Rooting depth.
Rooting depth. Okay. What else?
The source of the precipitation.
Sorry, what did you say? Yes.
I was going to say the source of the precipitation.
Okay. I heard another over here.
Filtration rate.
What I could
Infiltration rate.
Infiltration rate. I'm going to lump that in with rooting depth, but I'll just put it down. Okay. Anything else?
Evaporation.
Evaporation.
Yeah.
Bingo. Those are the major, yes, ma'am?
No, I was going to say the recycling between the canopy and the soil that is involved in
Yes, but right now we're just talking about the sources. You're getting just 2 steps ahead of me. So those are the major variations. The fact that you can have different sources of precipitation. Sometimes it's applied, sometimes it's natural. You can have water isotopically evaporating. Okay. Changes in the source, winter versus summer. Those are the biggies. So that means when some of you don't have your name tags on, so I can't look at you and say, you know, Edna, because I know my wife's name is Edna, so it's easy to remember. Edna and John, because I know John is from Hong Kong, you should be able to tell me how the variation in the isotope ratio of precipitation changes from winter to summer. What changes do I see?
So it would, as it gets cooler, it's going to get more rich. I'm trying to think of it as it moved up the gradient north as it gets cooler. That source is going to get more depleted.
So in winter, do I expect more depleted or more enriched?
More enriched.
In winter, more enriched or more depleted? More depleted.
Depleted.
Summer, more enriched.
Because you get more evaporation out from the source to the new source.
Well, the source is more exhausted. The fraction F is less because most of the water is rained out over the Sierras, the coastal range,
Before it gets.
before it gets here. Whereas summer rain tends to come from the Gulfs, the warmer regions. So we get variations in that water source. And aha! Now this leads me to irrigation. Where do I get my irrigation water from? Groundwater? Okay. And reservoirs. Oh my gosh. If I get my water from groundwater, it might fall on the meteoric water line. If I get my water from a reservoir, it might be isotopically enriched following the Craig-Warren model. Okay?
When the water from the deep well in the aquifer.
So if it's water from a deep well in an aquifer, it's likely going to be from penetration from the rain events, likely to be on the meteoric water line. And groundwater is likely to represent the mean weighted contribution over the course of the year. So you need to get that water down deep. In order to get that water down deep, we need to go to our next stage. And now I need 2 volunteers. Corinne doesn't have, Karina does not have her name tag on. violating rule number 1. I was forced to take my job. But Karina, can you come up to the front? And Rolla, can you come up? Okay, so you are going to be our group assistants, and you're going to take and help walk us through this exercise. So each of you grab a piece of chalk.
John.
No, this board here. And Karina is going to be responsible for graphic number 2, the isotopic composition of precipitation with depth. And Lola is going to be responsible for moisture content. Okay? So draw your axes, and then you guys are going to help these young ladies. I'm going to tell you that the isotopic composition, it doesn't have to be exact. The isotopic composition of the rain event you're about to see is minus 15 per mil. It's a rain event in the winter. Being an Isotope wannabe, I waved my hand over the rain water as I was coming out to go to the bookstore, and I predict it's like minus 10. I didn't collect the sample at home this morning, so we can measure it. Now, you have a dry profile and you're adding rain. And you're adding so much rain that you're going to saturate the profile. So I want you each to draw. So you're drawing soil water content. Draw what the profile looks like after this rain event that has completely saturated everything down to the bottom. This is the easy part, right? You want to help them? Got your straight line?
Straight line.
Okay.
Towards the right side.
Yeah.
Well,
Never.
for
No, for the soil water content.
soil water content.
So let's give you a little bit of an axis here. Minus 15, minus 5, 0. 0, 10, 20. And I'll help you and tell you that 20 is saturated. So what does our line look like? Straight line. Okay. So what, have them draw their line, help them.
So start at, for soil water content, start at 20.
Go to 20 and start at 20.
Straight down.
Yeah.
You said the depth.
Should be diagonal. No.
No.
Like you said, it's
Saturated. This is a gully washer.
Yeah,
It's saturated
it's
the entire
saturated all the
soil.
way to the bottom of the soil, so.
Yeah, straight down. Yeah. Okay. Now, what's the isotope ratio for precipitation going to look like? Same. Straight down. Beautiful. Okay. This is the starting point. The system is totally saturated. Now, just like today, it is just gully buster wet. You know, it's 3, 4, 5 inches of snow at Alta. But you know what it's going to be like this afternoon? It's going to stop raining. And tomorrow, it'll be 80. By the end of the week, it's going to be 90. And now what's going to happen? No further precipitation. But we're going to see evaporation. So let's first help Rolla. Imagine that it rained today and that it's hot for the next week. What do we expect the soil water content profile to look like if we only have evaporation?
More like
Moving towards 0.
As you go.
Okay?
Towards the top.
Mhm.
Yeah, 0 towards the top.
Okay? I won't quibble over the shape, but I think she has the concept
like this.
right. You know, I would probably modify this a little bit and say, you know what happened? It's evaporated, but it hasn't all evaporated. That only the upper layers have evaporated. Okay? And over time, evaporation comes from the surface and the moisture is supplied from below, so the moisture levels down below would decrease. Now, we need Karina to tell us what the isotopic composition of precipitation of soil moisture will look like, given what Rolla has given us as a change in water content. And you're simply applying what you heard from Gabe Bowen.
It's gonna be enriched.
It's going to be enriched, okay?
No.
No.
It's like a
Yeah, so let's start down deep, Once you start at the bottom, what's it going to look like? 15,
Yeah.
okay? So make it a dashed line and begin to increase in elevation. Okay, now what?
So
Should veer to the right.
the opposite of
The opposite pattern is you.
The opposite pattern. So it will, no, it will look like this. Is that right? So let's thank Karina and Rolla for their great highlights. They have established the fundamental pattern that you're going to see. Water evaporates not from depth. Water evaporates from the surface. And as water evaporates from the surface, the lighter isotopes are going to evaporate at a faster rate than the heavier isotopes. And as the lighter isotopes evaporate, the residual volume is going to be isotopically enriched. That's the profile you should expect to see if a soil evaporates and the change in its isotopic composition. Now, I mention this because this now becomes the important part of establishing a pattern. Now, the pattern that we have right here is the pattern I expect to see in the winter when we have rain events that are now minus 15. Okay? Who can I pick on right now? Julia. I would like to tell you that yesterday it rained. The isotopic composition of rain yesterday was minus 5 per mil. And you can make it a gully washer, or you can make it a light rain event. So I would like for you to come up, and I'll just tell you that's the gradient I've seen. And imagine for me what you think the isotopic composition of the rain would now look like. So we'd had some drying before, and now we've gotten rid of that drought by saturating it.
So we are still inside the soil?
So we're still inside the soil, and now I'm asking, with the help of your friends, you've got 45 friends out here, what do you think the isotopic composition of that rain now in the soil will look like?
When it towards the top of the soil column was more like negative 5 per mil, and towards the bottom was
Excellent. You draw
Other side?
no, so we draw this, so all you have to do is draw it here.
What did you say? So towards the top of the soil column, where we evaporated all of our previous negative 15 per mil water, now you're going to have mostly negative 5 per mil water. And then towards down in the soil column, beneath the depth where you didn't have full evaporation, it's going to start to mix.
That make sense? Yeah. Make big circles for us.
And then it'll start to veer to the left.
And then it will veer to the left. Okay,
Yeah.
excellent. Now, what Julia has established for us is that if you have winter rain events and you have summer rain events, you can get an isotopic profile in the soil. So, observation number one might be, I measure water that's taken up by roots, and I get a minus 5. Thank you. Get a minus 5. Sometimes I get a minus 10. And the first thing that Jed's going to say is, how good are your data? And if your data are good, and you have good QA/QC, we will never argue over the values you obtain. But we could argue over the interpretation. John in the back might say, man, species A, it's got a huge isotopic fractionation during uptake. Species B does not. Rose might more likely say, is it possible that plant A is getting its water from one depth and plant B is getting its water from a different depth? So we can argue over the interpretation of the data, but not of the data. The important thing for water sourcing is to remember that we can charge the profile with different rain events. And in fact, I predict if somebody did a project now in which they were looking at the water sources today, maybe tomorrow, they would find big contrasts between plants that take water out of depth and plants that take water out of the surface. I'm not a plant, I'm actually an insect. I'm drinking water in little pools. The isotopic composition of me as an insect will change because what I'm consuming might have had a value of minus 15 or might have had a value of minus 5. And that's a very labile, a dynamic signal. Now, for the sake of time, I'm going to be the guilty student up here. And I'm going to ask you to tell me what the isotopic composition is going to look like when I now look and do a plot. 2H at 18O minus 15, 0, minus 120, 0. What's the isotop? And here's the meteoric water line. What's the isotopic composition of all these different data points going to look like? Evaporation line, okay?
Below the photometer.
Okay. So I'm going to have a source value right here, because that's where it rained. And I'm going to have a source value right there because it's rained. And then all my points should come from there. And in fact, because I'm pretty lazy and I don't want to measure soil water content, I might be able to take the Rayleigh distillation model and invert it to calculate the fraction that's remaining and therefore soil water content. So I might be able to measure the isotope ratio and determine water content, knowing the values that have come in. Now, you can actually do this using a little device that Craig Cook invented. Well, he didn't invent it, he named it. It's called a dog bone. And a dog bone is a tube that goes into the soil and measures the isotopic composition of the water or the vapor at that particular depth. Okay. And it does it because the only way that gas can get in is from that particular depth. You can talk about this more with him. So this is meant to be an introduction to probably the most obvious pattern that you see in soils. They enrich very quickly over time. Now, if we begin to look at the more complicated part, you discover that, oh, okay, so we've got water coming in, a certain isotopic composition, maybe surface soils and deep soils and the aquifer have different values, so there's different water sources. If there's no fractionation during uptake, that's going to be the value of the plant. But wait a second, water is evaporating from the soils. Now I've got water coming in at +3 or -6, and he's claiming that the isotopic composition of the water that evaporates is -31. Raise your hand if you agree. Raise your hand if you disagree. Raise your hand if you're listening to me. Would you believe it? If they said -31 for evaporating water? I'm not arguing with the data, so maybe I am asking to argue with the data. If you argue with the data, you're wrong. The value is going to be -31. Why is it so different? It's because the light isotopes are the ones which are left to, it's the light ones. No, wait a second.
It should be.
Yeah, I would argue with that.
The light should be
Yeah,
evaporated.
I would argue with that. I would argue with that. I won't argue with Todd because he's not here to defend them, and Roxy would argue. Okay, Roxy, in private session, you're going to have to defend Todd Dawson because you are Todd Dawson's student.
I know, I can't remember what specific data this is from. This, if it's from like California, like deep water data in the critical zone, like, I don't know.
I don't know, so I won't let them explain it.
Yeah, I don't.
But what I will tell you is the one thing which I like in this data set here is the leaf water. Leaf water is enriched. Because it's going to follow the Craig-Gordon relationship. Okay, questions other than those that you want to direct to me?